Ethine, commonly referred to as acetylene, is an important feedstock for the synthesis of a variety of organic chemicals and polymers. It is mainly produced from the steam cracking of hydrocarbons or partial combustion of natural gas. In such processes, CO2 is a co-product and needs to be removed to produce C2H2 that is desired by industry. Industry demands C2H2 purities in excess of 99%. And in this presentation, we examine pressure swing adsorption technology for C2H2 CO2 separations and how to evaluate MOFs for use in such PSA units. MOFs for C2H2 CO2 separations fall into two classes. Most commonly, the MOFs are selective to ethine, which is the desired product, and a PSA scheme for producing C2H2 of the desired purity, typically higher than 99% plus, consists of a four-step scheme in which we have pressurization of the fixed bed adsorber, the adsorption phase in which the feed mixture is fed to the adsorber, and CO2 in relatively pure form is withdrawn from the top. This is followed by a co-current purge or co-current rinse step in which a portion of the product C2H2 is used to purge the CO2 that is present within the pores of the adsorbent and within the void spaces. This purged gas is then mixed along with the feed mixture and forms the feed to the adsorption phase. Following the co-current purge, we have a countercurrent vacuum blowdown in which the desired product C2H2 is withdrawn. Any CO2 remaining in the void volume will contribute to low purity of the product, and that is the reason we have the co-current rinse or co-current purge step. For evaluating MOFs that are C2H2 selective, we need to consider a PSA scheme such as the one shown here. And I discussed this in detail in my video presentation, Evaluating MOFs for C2H2 CO2 mixture separation, on my YouTube channel. Today I focus on CO2 selective MOFs for separation of mixtures of C2H2 and CO2 with the objective of producing purified ethine. In a development that is published in the Journal of American Chemical Society in 2023, the performance of an ultra microporous metal organic framework, Zn-ox-mtz, with functionalized polar groups within the ultra microporous framework is described, the pores are such as to allow for a significantly higher uptake of CO2 in comparison to C2H2, with the result that purified C2H2 can be recovered in the absorption cycle of a PSA scheme. This allows for higher product purities to be achieved at high C2H2 productivities. In this graph, I compare the transient breakthroughs of 50-50 C2H2 CO2 mixtures with use of 4 different MOFs that are all selective to CO2. The green squares represent experimental data for ZU610A. The blue lines refer to the experimental data for cerium MIL140 4F. The red lines show the experimental data for ultramicroporous Y BPTC that relies on absorption diffusion synergy for separating C2H2 CO2 mixtures, in which both absorption and diffusion favor the uptake of CO2. The crosses represent the experimental data for Zn-ox-mtz that is described in the JAX paper that is available online since a day or so. The data on transient breakthroughs are compared by using a modified time parameter that consists of a product of the flow rate of the gas mixture at the inlet, say in units of liters per second, time the actual times in seconds divided by the kilogram of MOFs that is packed inside the tube. The units of the x-axis is liters per kilogram. This is a convenient unit to compare experimental data published by different authors, in which the flow rates are different, the dimensions of the breakthrough tubes are different, and the amount of MOF packed into the tubes are different. This modified time parameter corrects for all of that and is convenient to compare the breakthrough experimental data. The time interval between the breakthrough of C2H2 that occurs near the beginning and CO2 that occurs towards the end of the breakthrough, that time interval is an indicator of the productivity of purified C2H2. And even a visual inspection of these breakthrough data curves would lead us to conclude that Zn-ox-mtz is the best MOF for producing purified C2H2 from 50-50 C2H2 CO2 mixtures. And the productivity of purified C2H2 is 2.09 moles per kilogram.